So we'll start the second part of the session. So we will have a first talk by Professor Enrico Boyom from Montpellier University. And so I give the floor to him on canonical Hamiltonian system in symplectic statistical manifold.
Okay. Thank you.
Tu peux avancer comme ça, le bouton vert.
D'accord. Merci. Attends, on fait ça.
Pour revenir en arrière, et le rouge.
Oui, pour monter sur le vert. Ok.
Essaye de bien tenir 20 minutes.
Merci.
Et parle bien dans les micros parce que...
Ok. Okay, thank you. So, here I'm going to talk about what I call Hamiltonian system in a manifold, in a symplectic manifold. It's a space of functions which are in evolution. You can consider the range of this system. If it's maximum, it is at most the half of the dimension. Then it defines Lagrangian foliation, the first Lagrangian foliation. Now, the reason why I enter this question is that it connects to many talk here, many reflections here. Okay, I will use two from algebraic topology and some differential topology also. Algebraic topology means that I will be concerned with cohomology space, cohomology class exactly. And when I have cohomology class, I have to interpret it as obstruction to the existence of something. So, the main question I interest is, the first question is the symplectic foliation in statistical manifold. This means that you have foliation, the leaves are statistical submanifold, and there are also symplectic manifold, and the connection of the statistical structure is a special connection of the symplectic form on the leaf. So when this connection with this formation is trivial, this means that there is only one leaf, which is the wall manifold. So you have a statistical, you have a symplectic structure which is compatible with the statistical structure. That means the connection we define the statistical manifold is a connection it is symplectic connection. It is symplectic connection. Why this question? This question is a tool to construct Hamiltonian system. To construct Hamiltonian system. Another reason why is what is called the recursion operator. That means if you have two symplectic structures on the same manifold, you have the Joule transformation, that means isomorphism of tangent band, we exchange them. This application is called recursion application. And in good situation, the spectrum of this recursion connection is a Hamiltonian system. Then there is important question, which is open question, how to relate recursion operator to Hamiltonian system. Okay. So, okay, I use the two, this is other two is what is the symplectic structure, homological structure. I say that we work with symplectic with the algebraic topology, that means with the cohomological class. Okay. What are the cohomological classes I'm interested in? you consider the Lie algebra of vector field of the manifold. These have many Lie subalgebra. And they have the same tensor module. In particular, if I take module of type 2, 1, this means the linear application, bilinear application of the tangent space in itself. I take the section of this. This is a module for every subalgebra. Then you can consider for every subalgebra of vector field the Chevalier-Elbicke cohomology with this in the tangent space. And imagine the forest, this universe, where you have a category of subalgebra, of Lie subalgebra. And all of them have the same Leaf module, which is the tensor of type 2, 1. Then I will construct some canonical class, module class, of subalgebra with coefficient in this tensor space. And this canonical have been introduced by Kozu, which is why I call it Kozu class. But Kozu defined two canonical class in some manifold. The one I'm going to talk about, and the divergence class. What is shown is that these classes are never vanished. They are never vanished in the manifold. So a manifold, different manifold, carry two, unless two cohomological classes, we never vanish. Okay, if you don't vanish, it is not very interesting. It is not, because you want to interpret a cohomological class of obstruction. That means if the definition means something, tell you some information. If it is not possible, because you say, no, now, this is not possible. But what is the origin of this class? What they come from? Okay, and it starts this thing. But if you consider now the category of Lie subalgebra vector field, for some subalgebra, this class, cohomology class, vanish. I want to interpret what means this vanishing theorem for the cohomology class. And this is related to Hamiltonian system. Okay, now, okay, the problem of compatibility of symplectic structure is also related, as I already said. You can interpret it also cohomologically. You can take fat condition for two symplectic structures being compatible. We define what it means compatibility. Okay, now the last question is some classical question. I want to seek for obstruction to the question. Under what condition a connection is metric? It's metric, it preserves a metric. A general connection, no Levi-Civita connection, it means high torsion. One which is metric. This is very hard question which is discussed for the car of torsion-free also. Because they had a torsion-free connection is a Levi-Civita connection, also metric. But it's very light issue. But I'm entering in general question. And the same question for symplectic manifold, symplectic structure. One, a connection preserves a symplectic structure. If you answer this question, but you answer the question of the existence of symplectic structure in manifold, a symplectic structure, because every manifold, every symplectic structure have many torsion-free connections. Don't forget global analysis, that is the existence of structure. I work in the Joe theory, that is the tangent space is morphism and the mechanism, some this pre-distinctive. That is what I do. Okay. So, now.
Le bouton vert.
Je peux faire ça. Alors. Okay. Now, my arsenal, my Uruguay two, come from George structure and George group. This is some prolongation of the talk of Barbara on the interest in the curvature and tangent band. Now I enter on the geotheory, that is tangent band a vector space. I enter is morphism and the interpret something. Now, so a George structure in a manifold is only a connection. It is tangent space under with a connection, or a cosine connection, or linear connection. And the George group is the open subset of the homomorph of this tangent band. Wall sections are inversible. George group is not a group. It is not a group. It is a fibration. Walls, fiber are Lie. That's a George group. And what is important is the notion of you have the notion of George equation in a statistical manifold. You have a definition here. You have a definition of George's connection. Take this operator, which is defined in the vector space of George morphism or George homomorphism. I don't know what he means this situation with this means solo. Okay. And I'm interested in the equation phi f nabla g equals 0. The solution of this. This is the set of solution of this equation is denoted by g nabla g. Okay, now, what is the causal tensor? The causal functor of this. Okay, you take every solution of George's equation, give rise to two other solutions. Phi, small phi, and big phi, big phi star. And they are defined what it, how you see here. Yeah. The definition of that, the operator. Okay. What is it is important to notice that it is not obvious that group phi and phi plus are solutions of George equation. They are solutions of George equation. So that we have to prove it. Now, okay, when you take a solution of George equation, you construct two least subalgebra of the vector field. It is the kernel of, you take the kernel of phi, for the group V phi, and the kernel of D phi. This is the sub-vector band of the tangent band. You take this section, you take algebra. It is an evolution. This is what I now put it. It is an evolution. That means that define two foliations. The first is Riemannian foliation in the general theory. It's Riemannian foliation. And the second is Symplectic foliation in the main theory. Okay. And this is a parenthesis. This equation, this theory, this approach, give a complete answer of the G's, ATN G's equation, question. How to construct all Riemannian foliation. The solution is given by this formalism, that you construct all Riemannian foliation for this one. And some key tool is the fact that if you take every singular Riemannian structure, that means a quadratic form which is of constant range, which is what is constant. It admits equivalent of Levi-Civita connection. That means it is preserved by torsion-free connection. But this connection is not unit. There are many ones. And this have to use fact to show that every Riemannian solution is obtained by this formalism. Okay. Now, if you take, I take this, the two algebra, G5 nabla and G5 nabla. Both have the space of tensor of type 2, 1 as left module. Then you consider the Chevalier-Hilbert complex with the coefficient in this module. And this complex, I will construct two cohomology class of dimension 1. They are given by the application. Yes, c'est ça. This is the derivative. Then you take the derivative of the connection. It is easy to see that it is a tensor. It is tensor 2-1 tensor. 2-1 tensor. You take it, and it is a cocycle. It is a Chevalier-Hilbert cocycle. What is important here? It is here cohomology class don't depend on the connection. You can change the connection. You can change other connection. We will get the 10th class. So to sort, if you change the connection, then the two cocycles you define are cohomologies. That the bit is the same cohomological class, the same algebra. So you can construct this functor. Solution of George equation, you take the corresponding cohomological class. So you have a forest of cohomological thing. We take, if you give the algebra of vector phi, you give it some cohomological class, some cohomological of dimension 1. I want to interpret this class. What they mean? This can vanish. If you take the whole vector phi, you take the class by causal, and it never vanishes, this class. But for other small, it can vanish. And now I want to interpret what means this vanishing class. Okay. Okay. No. Now, to interpret it, I said the notion of degeneration of this functor. I say that it is non-degenerate if the class is 0, means that the solution of George equation is 0. And this equation equals 0 means that we prove that. We mean that the kernel, that the algebra, this algebra is 0. It is 0. Then, seeing the application that is bijective, it is isomorphism. It is isomorphism. And this isomorphism would mean exactly that the manifold admit symplectic structure. But, this is the tone 5 of this one. Okay. Now, geometric structure in what if you say that if you take in statistical manifold, what means that it is symplectic? It means that you have a symplectic form which is parallel with respect to the connection. Remember that this is very, very important. If your statistical model is Hessian manifold, that means that the connection is flat, and his dual is also flat. It's also flat. Then you have two, in this situation, you have three things. You have what we call cohomology of the algebra Cauchy-Weinberg, with the first connection. You have the same thing with the second connection. Between the two, you have the Dayram complex. You have the Dayram complex. Okay, now, if you there is two in the curvy cohomology. What is the cohomology of algebra or Cauchy-Weinberg? There are two aspects. There's a restrict cohomology class and the total cohomology complex. They are quite different. The formula is the same, but they are very different. And the work, the efficiency is different. What are efficient in different categories. One answer the question, solve the conjecture of Gassenaber. The conjecture of Gassenaber tells you that if you have a restrict deformation theory, if you have to deform something, then there is this cohomology complex. We control this restrict deformation theory. What does this mean? This means that the restrict deformation theory that you define what you call deformation first. What you call infinite deformation. Second, you define. And what you mean trivial deformation. Okay, this is restrict deformation. Then if you have this situation, the conjecture says you have some cohomological complex which solve the question. And let me tell you what it means, the cohomological complex solving. This means that the infinitesimal deformation are cocycle of your complex. And if you have your deformation now is defined by some cohomological class. And the rigidity means that this cohomological class is zero. And the vanishing of the cohomological, it tells you that in fact, if you are deforming your structure in the same isomorphism class of structure. The rigidity being that when you deform some structure, the structure you obtain is isomorphic to the first one. Okay, I finished. Okay, now, okay, the compatibility now. The compatibility of two tensors, two symplectic mean that if you take the corresponding tensor product, you take the combination of this tensor product, you obtain two vectors, and this two vector is also a Poisson structure. It's Poisson structure. Okay, and this is what it means. Okay, I tell you that. Okay, sorry. The final result is that if you take solution of Joyce equation, you answer to this some cohomological class conclusion. If the cohomological class is zero, then you can define the cohomological class. Then the manifold, the statistical manifold, is a symplectic statistical manifold. More than that, this symplectic structure is obtained by use a inversive solution of Joyce equation. And you take the inverse of this. It is also a solution. It is a solution of Joyce equation, but for the dual symplectic, so dual statistic structure. And if you take the inverse of two, you construct two symplectic structures. And these two symplectic structures are compatible. That means, okay, yeah, this is the I thought to finish with this.
Okay, thank you, Michel.